I am Mr. Ish and I'm welcoming you to this video this evening. Thank you for joining me. Now we begin the examination of the tests of convergence. There are two which we will look at in this particular video. There are more, but in this video we're looking at the two basic ones. The first one I'll just call the basic test of convergence. It doesn't have a formal name, but according to the basic test of convergence, a series cannot be convergent unless its terms tend toward zero. What does that mean? If you have a sequence of items but you're looking at it in terms of series, and I'm just using this as a hypothetical, we're looking here at 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81 plus all the way up to 1 over infinity. You know what type of series. This is an infinite geometric series. But everything here in this video can apply to arithmetic series or even series which are neither geometric or arithmetic. And when you're looking at this, you're seeing that these terms are getting mathematically smaller. If you compute these on a calculator, they get smaller and smaller. So the series tends toward zero in terms of its value. It tends towards zero. In that case, you can say that this series is convergent. But the problem with the basic test is when you're talking about convergence, at best you can usually say it's maybe convergent because maybe it may not be convergent. But when you're using the basic test with regards to divergence, you can say it is yes. When you're saying it's divergent, you're good that it's divergent. But when you're indicating based on the test that you have a convergence, likely you could be right, but there's a chance that you may not be right, and that series might tend to be divergent. You want to look at this in a short-term way as this. When you're looking at this in terms of a limit as n approaches infinity, whatever term, the last term should equal to zero. In this case, you can say maybe we will be convergent. Maybe we have convergence. If you have the situation such as this, limit as n approaches infinity, these last few terms or the last term is not equal to zero, or your series is getting progressively larger in terms of its mathematical value, and you're not tending towards zero, then you know for sure we have divergence. And that's how, in a very basic nutshell, you can look at this basic test of convergence. If this is being seen, then maybe you have convergence, but if this is playing out, then for sure you have divergence. When you look at everything right here with regards to this specific scenario, if you have a series which looks like this, 1 and then 1 plus 3 plus 9 plus 27 plus 81 and then plus all the way up to infinity. In this particular case, when you look at this specific rule or this specific application in terms of the last several terms or the very many last several terms, you can see that in each instance you have a progressive increase in the value and you're not tending towards zero, but you're tending towards infinity. So here for sure you see divergence. It is for these type of cases here where you can with a reasonable certainty say you have convergence, but some series which look like this may tend to actually diverge and they may not be convergent. Hence, you would normally say maybe we have convergence. Then you would have to rely on additional tests to confirm that to be the case. I want to show you with regards to this basic test over here a situation where you have a exception play out with regards to something that seemingly appears to be convergent, but it ends up being divergent. A series might look like that in terms of an exception as something like this, and you'll see it to play out. We have 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. What can you do here in terms of a rule? You're looking at something, this right here, 1 can also be just as a 1 over 1. You're looking at something which is 1 over n, and you're always looking over here in this form 1 over n, where you're looking here from n is equal to 1 up to n to infinity. When you would open this up, you would have this. The first term is 1 over 1, second term is 1 over 2, third term 1 over 3, 1 over 4, all the way up to eventually 1 over infinity. Now look at this. When you're looking at this with regards to the basic test, the assumption is this. If you're looking at something like this from n equals 0 or n equals 1 up to infinity, and then you're seeing that the last few terms, I'm just indicating as this, is equal to 0, then you may expect convergence. The terms are progressively getting smaller. If you put these in your calculator, these are progressively getting smaller, and this value here is tending towards 0. Then why would it not be the case that this is convergent? It seemingly seems like it should be convergent, but the problem is this is one of those areas where the basic test of convergence fails, and this ends up being divergent, and I'll show you why. The way you show it is by means of grouping. And you would erase this because I'll add some more terms in terms of the grouping of those sequences. I'll add here 1 over 6, 1 over 7, 1 over 8, and then you would continue onwards. You would have to have a calculator to show this. When I'm doing grouping, I'm not grouping the first term, I'm writing it as such. I'm not grouping the second term, I'm writing it as such. Now I start grouping terms. I'll call this group made of 2 items group A. I'll call this group made of 4 items group B. Take the sum of that group A terms. You'll do 1 over 3 plus 1 over 4. 1 divided by 3 plus 1 divided by 4. I get 0.5833. I get 0.5833, so I know here A is a value larger than 1 over 2. We don't have to be specific by any means. Now let's take the group B term. I'll do 1 divided by 5 plus 1 divided by 6 plus 1 divided by 7 plus 1 divided by 8. I'm getting value 0.6345, and I know group B term here is larger than 1 over 2. If I were to round down this A value, which is larger than 1 over 2 to 1 over 2, from here I'm getting a 1 over 2. If I were to round down this term down to 1 over 2, from that group I'm getting a 1 over 2. Now if I keep making arbitrary number of groups where each time I'm clumping up a bunch of numbers to make a value larger than half, and then I round down to half, as you go up towards the direction of infinity, you can have an infinite number of groups, then you can have an infinite number of these 1 over 2's generate. And now look at this. When you look at everything right here with regards to the last term or the last few terms from 1 up to infinity, here you're not tending towards 0. What are you tending towards? You're tending towards half. You're never tending towards 0. So this seemingly convergent series ends up truly being divergent, and that's an area where this basic test fails. This series does not tend towards 0, it tends towards half. If you were to add up all of these, exclude even the 1, if you were to do an infinity in terms of the sum of these halves, you're still getting infinity as the total sum. You're just multiplying here in a shortcut. An infinite number of halves is still equal to an infinity, and that's why this ends up being a divergent, so the basic test fails. But anyhow, the basic test is not without its merit. Just keep in mind, limit as n approaches infinity, the last term or the last few terms, if they're tending towards 0, you may see convergence. But limit as n approaches infinity, the last term or the last few terms are not approaching towards 0, or your series is getting progressively larger, then definitely you have divergence. It's sure thing with regards to divergence, but it's not 100% sure thing with regards to convergence. And that right there is this test shown to you. Now we'll talk about one more test, and that'll be it for this particular video. The next test you want to be familiar with is this comparison test. It's a good test, it's not a bad test, but it's limited to those series which have positive terms, so keep that in mind. What's the basis of this? You have a series which is your test series, you're trying to test it out for convergence, we'll call that A. We have another series which is your known standard, and you need a known standard for comparison because you're comparing a test with a known standard. The known standard is already proven to be convergent. You're looking at a bunch of terms. You have an A1 term, you have an A2 term, you have an A3 term, you have an A4 term, and on and on. Likewise here you have a B1 term, B2 term, B3 term, B4. I'm writing these in the format of a series. The comparison test is basically like this. You're comparing an item by item analysis of one with the other, the test with the known. If each of the test items ends up being smaller than each of the corresponding known standard items, then for sure you have convergence because you're looking at something which is proven to be convergence. A1 being less than B1, A2 being less than B2, A3 being less than B3, and then on and on. You have some leeway that you can get away with a few of these beginning ones failing, but then the majority afterwards should correspondingly be smaller with regards to your test and the known standard. The known standard is already shown to be convergent. If these values are less than the corresponding values, then this must also be convergent by means of that comparison. That's the basis of this. But we have to show you a little bit more than what I'm saying here. So let's do it. If I were to put the comparison test in a sort of a format or a rule for you, I would do so in the following way. I have something here from 1 up to infinity. You don't want to be putting a 0 over here because you don't put a 0 in terms of a denominator, right? You don't do 1 over 0. So you would start here from 1. And you have n to the power of p in terms of the denominator. Specifically with regards to this p, you see right here in the denominator exponent, it can be greater than 1 or it can be less than or equal to 1. If it's greater than 1, you're going to see convergence. If it's less than or equal to 1, you'll see divergence. Why would that be the case? A p value less than 1 can very well be a negative value, like a negative 2. Think about something like this, 1 over 2 to the power of minus 2. You're looking here at 1 over you have a reciprocal coming out here, 1 over 4, and then you know you're getting a 4. Now what you end up seeing is something which was seemingly small has become something large in terms of its mathematical value. If you have these values with regards to what you see here in P, then you end up seeing your series flip. They undergo reciprocal, and you end up seeing an increase in the value, and you end up not tending towards 0, and you end up seeing divergence, which is why this specific test works well, especially when you have something of this appearance and you have a p-value which is greater than 1. How would this open up with regards to a series? You would have 1 over, your first term would be 1 to the power of p, plus 1 over 2 to the power of p, plus 1 over 3 to the power of p, plus 1 over 4 to the power of p, plus onwards up to 1 over infinity to the power of p. P here being larger than 1. It could be P could be 1.5, P could be 2, 3, what are these numbers, but they should be larger. And then now think about it, you have these numbers here and you're putting large P values, you're going to mathematically increase the value of the denominator 1 over that large number. These will very easily start becoming small numbers progressively, and they'll easily tend towards 0, and you'll see convergence. So you have to remember this particular case right here, P value greater than 1. A series that you're looking in terms of your test as something which looks like this, and then you would utilize a comparison test and you would compare to something which looks like this, which is known to be convergent. A shortcut situation can arise where you can eliminate most of this work, especially if you have a series which looks very familiar with regards to another convergent known series. If someone were to ask you to evaluate something like this, n is equal to 1 up to infinity from 1 over n square, what would you do here with regards to an assessment of it being convergent or divergent? Would you go through extraneous amount of work, or would you use a shortcut? I would use a shortcut, because when I look at this, it looks very much like that. When I look at this, it looks like a p-value which is larger than 1. Therefore, I can jump to the conclusion that this will be convergent. Because if you open this up in terms of a series, you'll have sequential terms which will mathematically get small in terms of their value, and it will indeed tend towards 0. So I'm looking at something which looks like this in terms of a comparison. I have a p-value larger than 1. I can jump to this conclusion that I do have convergence, and you can get away with that. Keep in mind, with the comparison test, you ideally will have situations where you will do an item by item analysis or corresponding analysis with each term, and I want to end this video utilizing the comparison test with regards to that. We will do a series analysis where we will be forced to do some form of analysis. Our test series is this, and let's put it out for you. It doesn't have to exactly match that, but it could mirror it. I'm looking at something which looks like 1 over n to the power of n, and I'm looking at everything here from 1, n equals 1, up to infinity. Now look, if I were to expand this out, what would it look like as n values increase? I have 1 over 1 to the power of 1, plus 1 over 2 to the power of 2, plus 1 over 3 to the power of 3, plus 1 over 4 to the power of 4, plus 1 over 5 to the power of 5, plus all the way up to 1 over infinity to the power of infinity. That's exactly what I have. Look at it, n to the power of n, n to the power of n. Now look at this basic premise that I put for you over here. If p was greater than 1, you have convergence. Other than the first term, I have p values greater than 1, and they're getting large. And you know, progressively these values mathematically will get smaller as you go in that direction, and you will indeed zero out. But what would be a good known standard series which would mirror this in terms of appearance and form, and we can compare it to in terms of item by item? You can compare it very easily to something like this, and let me put out for you. N is equal to 1. This is my known standard, which is known to be convergent. This is what I'm looking at. 1 over n to the power of p, where p is equal to 2. That's exactly what I'm looking at. So I'm rewriting this as 1 over n squared. This here is my template form, which looks kind of like that, except here in my n value I have a defined p value of 2. If I were to open this up, what would be my terms? I would have 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square plus 1 over 5 square plus all the way up to 1 over infinity square. I've mimicked this with regards to this in terms of the length I'm showing you. This series right over here is known to converge. You don't even have to show it to converge, but it's known to converge because it's one of those standard series of convergence, and it serves as a good known standard for which you will do this comparison with. Now we will do item by item analysis. Here's my first term, here's my first term. When I'm comparing the first term here, I'm getting a 1 and a 1, and I see a failure over here, the test value here is not smaller than your known value. When I look over here, I have 1 over 4, I look here, I have 1 over 4, and it fails again. The test is not smaller than the known standard. But when I look over here, I have 1 over 27, here I have 1 over 9. Now I know for sure 1 over 27 is indeed smaller than 1 over 9. You can do that on your calculator. So we pass that part. Here I have 1 over 4 to the power of 4. What's 4 to the power of 4? It's 1 divided by 256, which is definitely less than 1 over 16, so I pass over here. I have 1 over 5 to the power of 5, which is 1 divided by 3125, which is definitely smaller than 1 divided by 25, so I pass over there, and indeed this passes. Other than the first two terms, everything item by item, the corresponding analysis between the test and the known standard, the test values or the sequences are always smaller than their corresponding known values based on the corresponding standard values. And you can easily say that this will converge because your known standard which you're comparing to is known to converge. Therefore, by comparison test, you can say that this easily converges as well. Other than you overlooking the first one or two terms, that much leeway is acceptable. From here onward, we see these values being always less than these values, so you can say you have a convergence at play. Keep in mind the tests of convergence we've talked about are the basic test and the comparison test. With the comparison test, you want to look at something like this. The p-value should be larger than 1 and you will see convergence. If the p-value is less than or equal to 1, you will see divergence. With the basic test, as you remember, the series in terms of how it progresses, you should see a gradual decrease or a great decrease in the value. It should tend towards 0. If the situation is such that the values do not tend towards 0, you definitely have divergence. If the situation is such that you are tending towards 0, you may have a chance of convergence, but it's never 100% sure or a guarantee that you will see convergence because exceptions will fall into play. And that's all I want to present to you in this video, the two basic tests of convergence. There are more to look at in the future. Thank you for watching. Have a good day.